Dear students, in the last video we have discussed two string matching algorithms, the knife string matcher and the Robin-Karp algorithm. In this video we are going to discuss the initial introductory aspects about another string matching algorithm, the string matching with finite automata. Basically, this finite automata is a simple machine for processing information, and it scans the text string T for all the occurrence of the pattern P. And the algorithms are very efficient because they examine the text character exactly once, as compared to other algorithms such as the knife string matcher, which matches a particular character multiple times with the pattern. The time to build the automaton will be large, especially if the alphabet sigma is large. Now, a finite automaton M is a phi tuple, capital Q, Q naught, A, sigma and delta. Q is a finite set of states that make up the machine. Q naught belonging to Q is the start state. A is a subset of Q and is a distinguished set of accepting states or answer states, we can say. Sigma is a finite input alphabet. Delta is a function from Q cross sigma into Q called the transition function of M. That is, it defines if it reads a particular character from the alphabet, from a string, then if it is in a particular state, to which state it goes, that is given by the function delta. The finite automaton begins in state Q0 and reads the characters of the input string one at a time, and then transforms itself from one state to another state. If the automaton is in state Q and reads A, it moves to a state delta of Q comma A. And if the current state is a member of the accepting state A, then the machine has accepted the string read so far. You have a figure on the left side of the slide. Basically, it defines or it presents a simple finite automaton. It has two states, 0 and 1, and the alphabet for this particular what is called the finite state machine is A and B only. Initial state is 0 and the accepting state is 1, and all the states are only two states are there, that is 0 and 1. If it is in the initial states and it receives or it reads an alphabet A, it goes to state 1, and if it is in state 1 and it receives an alphabet A, and it goes back to state 0, and again if it is in state 1 and reads a character B, it goes back to state B, 0, but if it is in state 0 and reads B, it is going to remain in state 0, and that is defined by the function also and the table which we can call as the transition table. A finite automaton induces a function phi called the finite state function from sigma star, which is nothing but the set of all strings that can be produced, to Q such that phi of W is the state the machine M ends in after scanning the complete string W. Thus, the machine M accepts the string W if and only if phi of W belongs to the answer state A. We define phi recursively using the transition function delta. Phi of epsilon will be Q naught. Phi of WA is nothing but delta of phi of W comma A, and for all W belonging to sigma star and A belonging to sigma. String matching automata. In order to specify a string matching automata corresponding to a given pattern P1 to M, we define an auxiliary function sigma called the suffix function corresponding to capital P. Notice we are using small sigma to define the suffix function. The suffix sigma, the suffix function sigma maps sigma star to a value from 0 to M such that sigma of x is the longest prefix of the pattern P that is also a suffix of x, which is mentioned like this. Mathematically, we define sigma of x as max of k such that P of k is a suffix of x, and pk now defines the prefix of the pattern P. The suffix function is well defined as empty string is a suffix of every string. We define the string matching automaton that corresponds to given pattern P1 to M as follows. That is, the state is going from 0, 1 to M. That is, we are talking about the length. The length of the pattern is M. So it can be in state 0, or it can be in state 1, or it can be in state 2, and so on up to M. The start state Q0 is the state 0. The state M is the only accepting state. So if you are reading a text string T and you come to the state M, it means that you have read a pattern in the text. The transition function delta is defined by the following equation for any character A, that is delta of q comma A is same as sigma of pq comma A. The suffix function sigma and the transition function delta are related like this, which you can easily understand. What is the transition function? Transition function defines from which state q, from a given state q, it goes to which other state q dash when it reads a character A. Now the suffix function of pq comma A is nothing but it gives the length of the longest length of the prefix, which is also the suffix of the pattern pq comma A. That is, if you add this, how much you are going to end up with. So that is what is the transition function also, and it can be proved. Now this is a simple string matching automaton which we have constructed according to the definition we have just seen. The pattern is AB, AB, AC, A. Now initially it is in state 0, and at in a state 0, if it receives or it reads alphabet A, it goes to state 1. Now again at this in state 1, if it reads A, it again remains in state 1. But if it receives any other character such as B or C, then it returns back to state 0, but that is not shown in the diagram. That particular transition is not shown in the diagram, which goes back to the state 0. Similarly, at state 1, if you receive B, it goes to state 2, and in state 2, if A is received, it goes to state 3, and it continues like this. You can understand how the transition, what you call the finite state machine is going to be built. The transition table is also given over here. The transition table states that in state 0, the alphabet for this particular finite automaton is A, B, C, and A, B, and C only. So what happens is in state 0, if there is it receives a character or reads a character A, it goes to state 1, and if it is anything else, B or C, it remains in state 0. Similarly, if it is in state 1 and reads A, it goes to it remains in state 1, and if it reads B, it goes to state 2, and if it reads C, it goes to state 0. Only this going to state 0 is not shown in the diagram with arrows, but here it is clear. Now a simple example of the pattern matching and the output, it's shown over here. So initially you start reading the text. There was nothing, and first you read A, you go to state 1, then you read B, you go to state 2, again you read A, you go to state 3, and you read B, you go to state 4, A again, go to state 5, B again, go to state 4 back. Similarly, when you reach 7, which is the answer state, we have found the string. It is easy to decipher from this. That is how we build a string matching automaton. For any given pattern, we can similarly build the string matching automaton and the transition table. What you have learned in this slide is the introduction to finite automaton for string matching. In the previous video, we also discussed the string matching problem and notations, the naive string matcher, and the Robin-Karp algorithm for string matching. Thank you. In the next video, we'll discuss more about the finite automaton. Thanks once again.